In the year 1828, an amateur cartographer named Edward Quinn finished his magnum opus, the Historical Atlas. Published after his death, it portrays our knowledge of the world not as a static fact, but as a single, flickering light, a candle pushing back an oppressive, swirling fog. The clouds of ignorance. With each turn of the page, the fog recedes. The first plate shows only a tiny patch of light over the lands of the Euphrates and Tigris. The rest of the globe is shrouded. Time marches on. We see the Roman Empire. The fog has pulled back slightly. With each great human expansion, the dispersal of the clouds mirrors European discovery. By the early 19th century, the final plate, the clouds are fully dispersed. All the continents are visible. The map is complete. The implication is clear. There is no more land left to discover. The fog has been vanquished. Of course, this perspective is profoundly limited. For an artist in China or a navigator in Polynesia, the focus would be entirely different. Each had its own known world, surrounded by its own darkness. And indeed, these clouds are not solely geographical. They are conceptual. All human endeavors, from philosophy to science, begin in a fog of mystery. A fog that only begins to clear when we learn something new. Like the sheathed surface of the Earth, clouds of profound mystery have also shrouded our understanding of the universe. For millennia, we saw the heavens as a perfect, unchanging backdrop. But over the last few hundred years, we have turned our telescopes upward. We have peered deeper and deeper into the cosmos. We have spied galaxies, black holes, and planets. We have peered back over 13.7 billion years and seen the very afterglow of creation. We can even deduce the future history of our universe, looking forward to the heat death of the cosmos, when all matter melts and black holes evaporate. One by one, the universe has seemingly given up its secrets. The cosmic clouds have steadily been lifted. It might appear, once again, that we have reached the end, that we have learned all there is to learn. But we have been here before. In 1888, the celebrated astronomer Simon Newcomb declared that we were nearing the limit of all we can know about astronomy. He died in 1909. In that exact period, a young patent clerk named Albert Einstein was publishing papers that would not just push the fog back, but set fire to the map itself. It is always a bad idea to bet against further discoveries. And so, this is where scientists find themselves now. Standing on towers of complex equations, they try to peer further into the fog. But this is not only a fog of distance. These are clouds that linger around us, within us, before us. These are clouds of possibility. These are new universes, potentially born beyond our cosmic horizon, or even splitting off from our own reality with every quantum instance that passes. As our knowledge of theoretical physics has grown, what was once dismissed as fantasy has gradually, stubbornly forced its way into the realm of possibility. Multiverse theories have proliferated. From parallel worlds of infinite U's to barren deserts of endless nothing, scientists are blowing away the cosmic fog of unknowing, revealing a warped, infinite Russian doll of infinities. Welcome to the multiverses. Our journey into this staggering idea begins with a simple, practical question. A question that just 1 century ago was the single greatest unsolved mystery in astronomy. Just how big is the universe? The date is April 26, 1920. The setting, the Smithsonian Museum of Natural History. The event is billed as the Great Debate. On the stage are two of the most respected astronomers of their time. In one corner, Harlow Shapley. He's the man who almost single-handedly mapped the true scale of our own Milky Way. He proved our sun was not at the center, but in a galactic suburb. To Shapley, this new, vast Milky Way was the entire universe. That was it. There was nothing beyond. Those spiral nebulae, they were simply swirling clouds of gas and dust, features buried within the stars of our own Milky Way. But Heber Curtis objected. He was no fan of this compact cosmos. He argued that the universe was large, much, much larger. The spiral nebulae, he declared, were not within the Milky Way. They were, as the philosopher Immanuel Kant had speculated, island universes, individual galaxies, just like our own Milky Way, home to their own billions of stars. Curtis's key piece of evidence was observational. He had found novae, exploding stars, within the Andromeda Nebula, and these novae were faint, suspiciously faint. If they were the same type of explosion as the novae in our own galaxy, their faintness must be due to an immense distance. He argued they must be many millions of light years away. But things were changing, and changing quickly. A new astronomer, a former lawyer named Edwin Hubble, had recently joined the staff at the Mount Wilson Observatory. He was on a personal quest to answer this very question. The timing was fortuitous. The world's largest telescope, the 100-inch Hooker, had just been installed. Hubble's first target, Andromeda. He too knew the entire debate rested on one question: just how far away are the stars in that nebula? To solve this, Hubble needed a standard candle, a type of star whose true, intrinsic brightness was known. He was not searching for novae. He was scouring Andromeda for a particular kind of star, a Cepheid variable. The key to these stars had been discovered just years earlier by a woman named Henrietta Swan Leavitt. Leavitt worked at the Harvard College Observatory as a computer, one of several women hired to perform the laborious task of cataloging photographic plates. While examining plates of a nearby galaxy, Leavitt noticed something profound. She identified many Cepheid stars and painstakingly measured their brightness and the time it took for them to pulse, their period. And she found an ironclad relationship. The brighter the star was intrinsically, the slower it pulsed. This was a breakthrough of monumental importance. Henrietta Swan Leavitt had discovered the universe's yardstick. Her period luminosity relationship meant that if you could observe a Cepheid variable star anywhere, measure its beat, you could deduce its true luminosity. And by comparing that to how bright it appears, you can calculate its distance. It was these standard candles that Edwin Hubble was hunting for, and in October 1923, examining a photographic plate of Andromeda, he found one. He tracked its regular beating pattern. He measured its period. He then used Leavitt's law to calculate its luminosity. The picture became crystal clear. The star he was observing, V1, was an incredibly bright giant star, but it appeared pathetically faint. For it to be that luminous, yet appear that dim, it had to be located at a distance of nearly 1 million light years. This was a number so vast it shattered every contemporary model. It was far, far outside the most generous boundaries of Harlow Shapley's Milky Way. In 1924, Hubble sent a letter to Shapley, politely but devastatingly informing him that Andromeda was not a gas cloud. It was a galaxy in its own right. And if Andromeda was a galaxy, then the other nebulae must also be galaxies, each at an immense distance. The great debate was settled. Curtis, the island universe proponent, was correct. And Shapley's response upon reading Hubble's letter? He famously turned to a colleague and said, "Here is the letter that destroyed my universe."
The clouds on Quinn's atlas, the ones that had been so neatly brushed away, suddenly rushed back in, revealing not a finite, completed map, but an ocean of unimaginable size. Our cosmos suddenly became much, much bigger, and our place within it, infinitely smaller.
Throughout the 20th century, we continued to peer deeper into this new, vast ocean. Hubble's millions of light years became billions of light years. We pointed the Hubble Space Telescope at a patch of sky that appeared completely black. The result was the Hubble Deep Field, not an empty void, but a canvas filled with 10,000 galaxies, stretching back almost to the beginning of time. But was there a limit? Was there an edge to how far we could see? In 1964, there was a chance discovery. Two radio astronomers at Bell Labs, Arno Penzias and Robert Wilson, were plagued by a persistent low-level hiss in their antenna. It came from every direction in the sky, day and night. They cleaned their equipment. They even scraped out what they described as a white dielectric material, pigeon droppings. The hiss remained. Meanwhile, just down the road at Princeton University, a team of physicists led by Robert Dicke was building a detector to search for the one thing that would prove the Big Bang Theory correct: the leftover heat, the thermal afterglow from the creation of the universe. When Penzias and Wilson learned of Dicke's work, they realized what their hiss was. It was not a flaw. It was the oldest light in the universe. It was the afterglow of creation. This discovery, the cosmic microwave background, or CMB, marked the limit of our observations. It is a literal wall of light. We cannot see past the CMB with any telescope, because in the era before it was emitted, the universe was an opaque, superheated plasma. The light from the CMB has been traveling for 13.7 billion years to reach us. This marks the edge of our observable universe, a boundary, a horizon between the cosmos we can see and whatever lies beyond. This, of course, leads us to ask the most profound question in modern cosmology. Just what is beyond the observable universe? Theorists had already been at work. Building on Einstein's equations, they realized that our observable universe must only be one part of a much larger whole. Beyond that observable horizon, there must be, well, more universe, more galaxies, more stars. But how much more? And it is here that we meet the first of our infinities and the first level of the multiverse. Our best cosmological measurements, particularly from the Planck satellite mapping the CMB, show the universe to be geometrically flat. If the universe has no spatial curvature, the simplest and most likely topology is that it just goes on forever. This might seem strange given the Big Bang, but the Big Bang did not happen at a point in space. It happened everywhere in space at once. If the universe is spatially infinite today, it has always been infinite, even at its birth. It began as an infinitely large, infinitely dense cosmic egg. All we can ever observe is this small patch around us, our observable universe, embedded within this infinite, expanding whole. But at the end of the 20th century, everything changed. Astronomers announced the completely unexpected discovery that the universe's expansion is not slowing down. It is accelerating. The culprit was named dark energy, a mysterious, repulsive force. It was realized that galaxies were, and are, moving away from each other faster and faster. What did this mean for our observable universe? It meant our map
which had been expanding, will once again be plunged into darkness. As time marches on, we will begin to lose sight of distant galaxies. The accelerating expansion will carry them away from us faster than their light can travel to us. In about 100 billion years, a future astronomer on Earth will look up, and they will see nothing but the stars of our own local galaxy. Beyond that, there will be only the blackest black. At every moment, there is less and less of the total universe we will ever be able to explore. Astronomers estimate that 99% of the galaxies we can see in our observable universe are already out of our physical reach. We will never, ever arrive. But though we will never visit these distant worlds, we can use pure logic to deduce their properties. Let's stick with the simplest picture, that beyond our horizon is an infinite space, governed by the same laws of physics. Let's call our observable bubble a universe. Beyond our horizon, there are countless other universes or patches, each with their own observers, each causally disconnected from us forever. What do we call the entire thing, the infinite expanse that contains this myriad of universes? Welcome to the Level 1 Multiverse. The physicist Max Tegmark calls this a Level 1 multiverse. It requires no new physics. It is the simplest, most direct consequence of an infinite universe. But if we follow this logic, a disturbing and profound picture emerges. In our Level 1 multiverse, each individual universe, or Hubble volume, contains a finite number of atoms, which can be arranged in a finite, albeit astronomically large, number of ways. The number of possible quantum states for all the particles in our observable universe is vast, but finite. It is roughly 10 to the power of 10 to the power of 118. But in a Level 1 multiverse, you have an infinite amount of space to play with. If you have an infinite number of lottery tickets and a finite, though huge number of possible winning combinations, you are guaranteed to have infinitely many winners. Every single possible combination must occur, and it must occur infinitely many times. Out there in the void, some of these universes will be identical to ours, absolutely precisely quantum state for quantum state the same. In this other universe, there will be a Milky Way, a sun, and an Earth. And on that Earth, there will be another version of you watching this exact video at this exact moment. How far away is this doppelganger? Tegmark estimates something like 10 to the power of 10 to the power of 118 meters. A number so large the human mind cannot grasp. You will never interact with them, but they would be out there in the infinite quilt of reality, along with every possible variation of you. A universe where you took that job. A universe where you didn't. Anything that has a zero, non-zero chance of happening must happen in the infinite Level 1 multiverse. And yet, this is just the beginning. This is just Level 1.
Why does our universe have its particular laws of physics? This might seem like a strange question. How could it have been otherwise? But as our knowledge has advanced, this question has become the most vexing problem in all of science. It's called the fine-tuning problem. In the 1960s, cosmologist Robert Dicke
the same man from the CMB story, suggested that the forces of gravity and electromagnetism were finely balanced. If gravity were just a tiny bit stronger, the universe would have collapsed back on itself. If it were a tiny bit weaker, stars and galaxies would never have formed. As physicists stared deeply into their equations, more examples of this fine-tuning were revealed. Astronomer Fred Hoyle was trying to figure out how stars create carbon, the basis of life. He realized the only way was through a very specific three-step triple alpha process. For this to work, the carbon-12 nucleus needed to have a very precise energy level. He told his colleagues to look for it, and to their astonishment, they found it, exactly where he said it must be. Hoyle realized that if this resonance level were different by even a few percent, stars would produce almost no carbon. The universe would be sterile. The list goes on. Serendipity piled on top of serendipity. If the strong nuclear force were 2% weaker, protons wouldn't stick together, and hydrogen would be the only element. If the mass of the neutron were slightly different, all protons might have decayed, leaving a universe with no atoms at all. And then there's dark energy. Our best theories predict it should be 120 orders of magnitude stronger than it is. If it were that strong, the universe would have ripped itself apart in the first fraction of a second. It became apparent that if our universe was even very slightly different, we simply would not exist. Our cosmos appears to have just the right physics, just right parameters to allow for the complexity of life. And it is in that key adjective that the answer may lie. Our cosmos. It is through this problem that we can take our first steps into the Level 2 multiverse.
There are many ways to build a Level 2 multiverse, but we will start with the most dominant idea in modern cosmology: eternal inflation. Originally proposed by Alan Guth, inflation was a theory designed to solve some of the puzzles of the Big Bang model. Why is the universe so geometrically flat? Why is the CMB so perfectly uniform in temperature? Guth's solution was radical. He proposed that in the first trillionth of a trillionth of a trillionth of a second after the Big Bang, the universe underwent a period of hyper-expansion, driven by an inflaton field. This burst of rapid expansion would have smoothed out any initial curvature, making it flat, and blown up a tiny, uniform patch to be larger than our entire observable universe. But physicists like Andre Linde and Paul Steinhardt refined the theory. They realized that inflation wouldn't end gracefully everywhere at once. While in some places the inflaton field would decay and create the Big Bang, in other places quantum fluctuations would keep the inflation going. This new theory of inflation, called eternal inflation, embraced the messiness. In this picture, inflation never ceases. It is an eternal, self-reproducing, fractal-like process. As the cosmos inflates, individual universes continually crystallize out of the inflation, like bubbles forming in a boiling pot of water. In this picture, our entire Level 1 infinite multiverse is just one of these bubbles, one of countless many, separated from all the other bubbles by an ocean of eternally inflating spacetime. And here is the key. It is this bubble nucleation that cements the properties of the universe it forms. This includes the very laws of physics themselves. In this model, when a new bubble universe forms, the fundamental constants, the particle masses, even the number of spatial dimensions, can crystallize into a different configuration.
This means that in some universes, the forces of nature will be different. In others, there might be more or fewer dimensions of space and time. Physicists have wondered what these other universes would be like, and they have arrived at a stark, sobering conclusion. Virtually all of these other universes would be dead and sterile. But within this endless churning sea of dead universes, there would be tiny, rare pockets of habitability, the lucky bubbles where the roll of the dice landed on parameters that do allow for stars, carbon, and complexity. And it is no surprise, the theory states, that this is where we find our universe. The apparent fine-tuning of our physical laws is, in this view, little more than a statistical fluke, an anthropic selection effect. We won the multiverse lottery, and that's the only reason we are here to wonder about it. This is the Level 2 multiverse, a collection of disconnected bubble universes, each with its own fundamental laws of physics. This idea is supported by another, even more complex theory, M-theory. Born from the ashes of 5 competing string theories, M-theory was unified by Ed Witten. This theory, which lives in 11 dimensions, doesn't just allow for different universes, it demands them. M-theory predicts a string theory landscape of possible solutions, at least 10 to the power of 500 different ways for the extra dimensions to curl up, each one creating a universe with its own unique laws of physics. In this view, eternal inflation is the engine that creates the bubbles, and the M-theory landscape is the die that is rolled, deciding the laws for each new universe as it's born. And so the fog has retreated to reveal a plethora of possible Level 2 multiverses. But is this as weird as it gets? In a word, no.
What if I told you that you are immortal? That you will, in a very real sense, live forever? What if I told you that with a gun pointed at your head, loaded for a game of Russian roulette, I could ensure your survival? You might think I am mad, but we have now arrived at the Level 3 multiverse, and here, immortality is guaranteed. To understand this, we must leave the realm of the very large, cosmology, and enter the realm of the very, very small, quantum mechanics. We begin with the experiment that broke physics, Thomas Young's double-slit experiment. In 1801, he shone light at a screen with 2 narrow slits. If light was a particle, he'd get 2 bright spots. But if it was a wave, he'd get a complex interference pattern of many bright and dark stripes. He set up the experiment, and he found the beautiful, rippling, striped pattern of interference. The conclusion was indisputable. Light was a wave. This viewpoint lasted for a century. Then quantum physics came along and muddied the water. Einstein proved that light also behaves as a particle, a photon. This left scientists with a schizophrenic problem. How can light be both a particle and a wave? This duality, we now know, applies to everything. Electrons, atoms, you. Everything is both a particle and a wave. In the language of quantum mechanics, an electron is described by a wave function. This is a wave of potential smeared out over space. In the double-slit experiment, the electron's wave function travels, passes through both slits at the same time, and interferes with itself. But not quite. Let's run the experiment again, but this time fire one single electron at a time. The single electron leaves the gun. It travels as a wave function. It passes through both slits. But when it hits the final detector screen, it doesn't register as a smeared-out wave, it registers as a single tiny dot, a particle. The electron travels as a wave but interacts as a particle. How? How does this smeared-out probabilistic wave function decide to become a discrete electron at this specific spot? This is the measurement problem, and it is the rotten core at the heart of quantum physics.
The first solution was the Copenhagen interpretation from Niels Bohr and Werner Heisenberg. They argued that the wave function is a wave of probability, and that this wave evolves until it is measured by a classical macroscopic observer. At the moment of observation, the act of looking forces the universe to make a choice. The superposition of possibilities collapses, the dice is rolled, and the particle snaps to one and only one definite location. This leads to bizarre paradoxes, most famously Schrödinger's cat. Place a cat in a box with a quantum-triggered poison. Until an observer opens the box, the atom is in a superposition of decayed and not decayed. Therefore, the poison is both released and not released. Therefore, the cat is both dead and alive. Only when the conscious observer opens the box does the wave function collapse, forcing the cat to be either dead or alive. To Bohr, this was just reality. To Schrödinger and Einstein, this was madness. This is where Hugh Everett III enters the story. In the 1950s, this Princeton graduate student looked at the measurement problem and proposed the most radical solution of all. His aim was to follow the maths of quantum theory. Real-world consequences be damned. Everett rejected the Heisenberg cut between the quantum and classical worlds. He realized the observer is also just a big bag of atoms, and those atoms must also obey the laws of quantum mechanics. And he threw the notion of wave function collapse right out of the window. Let's go back to Schrödinger's cat. In the Copenhagen interpretation, the cat is dead plus alive until we look, at which point it collapses to either dead or alive. In Everett's many worlds interpretation, the wave function never collapses. When the radioactive atom enters its superposition, it becomes entangled with the cat. The state of the box is now decayed atom and dead cat, plus undecayed atom and alive cat. When you, the observer, open the box, you do not collapse the superposition. You join it. You become entangled with the cat. The total wave function of the universe now evolves into two distinct, non-interacting branches. Branch 1, decayed atom and dead cat, and you see a dead cat. Branch 2, undecayed atom and alive cat, and you see an alive cat. Both outcomes happen. Both are real. The act of measuring severs the connection between these branches. Two separate universes have now become distinct. And in one of them, there's a version of you grieving for a dead cat. In the other, there's a version of you relieved to find an alive one. This doesn't just happen with cats. It happens at every quantum measurement, at every quantum interaction. Every single probabilistic outcome in quantum mechanics is played out. Individual universes with distinct futures crystallize out of this ultimate superposition. This is the level 3 multiverse. These other universes are not far away in space like level 1. They are right here, right now, existing in parallel in an abstract mathematical space, constantly branching off from our own.
Some physicists dismiss many worlds out of hand, calling it exceedingly wasteful. Everett's insights were largely ignored during his lifetime. He left physics a deeply embittered man. But his ideas resonated with a new generation of physicists. To some, many worlds represents the only realistic solution to the measurement problem. But there are still questions, not least of all, consciousness. What happens to the you as individual universes diverge? This brings us back to our gun to the head. It's a thought experiment called quantum Russian roulette, or quantum immortality. Imagine a quantum gun hooked up to an electron. If the electron is measured spin up, the gun fires. Spin down, it just clicks. The odds are 50-50. You place the gun to your head and pull the trigger. In the Copenhagen interpretation, the wave function collapses. Click, you survive. Or bang, you die. The outcome is random. Play this game 10 times, you are almost certain to be dead. But what happens in the many worlds interpretation? The moment you pull the trigger, the universe splits. In branch A, the electron is spin up, the gun fires, and you are killed. In branch B, the electron is spin down, the gun clicks, and you survive. Both universes are real, but you, your stream of consciousness, can, by definition, only continue in the branch where you are alive to experience it. The you in branch A is gone, but the you in branch B is very much alive, sighing of relief. You're instructed to pull the trigger again. Again, the universe splits. Branch B1, you die. Branch B2, you live. Your consciousness continues, unbroken, down branch B2. You pull the trigger again, and again. 1,000 times. In the vast majority of universes, you are long dead. But your specific, subjective experience, your unbroken stream of consciousness, will always find itself on the lucky path. The one future history that guarantees survival will always be the one you experience. From your perspective, you are immortal. You cannot die. You have just played quantum Russian roulette 1,000 times and survived every shot. You would be convinced you were a god. But in reality, you are just the lone, lucky survivor, standing on a mountain of your own corpses in a million other timelines. It may seem that we have come to the end. What could possibly contain more than the ultimate superposition of all possible universes? To get to this point, we have had to consider parallel doppelgangers, infinite bubble universes, and quantum branches splitting off with every choice. But to get to the next and final step, we have to completely and utterly let go of our ideas of reality itself. For in the level 4 multiverse, we will find that we and our entire universe may be little more than a mathematical dream. What is reality? As you look around, it seems obvious stuff. But you know this is an illusion. It is all just atoms. But we can strip back reality even further. Atoms are just electrons and quarks, and these particles are just properties. They are described by their interactions, their forces, and the laws they obey. And all of this, the particles, the forces, the laws, is written in the language of mathematics. Numbers, equations, vectors and tensors that describe this reality with stunning precision. But where do these rules of reality exist? Where is the Schrödinger equation written? And it is now that we arrive at Max Tegmark's Level 4 multiverse. This multiverse is not made of space, or time, or brains. This multiverse is filled with nothing but mathematical structures. It is the ultimate ensemble of all possible logical mathematical systems encompassing the entire realm of abstract possibility. These mathematical structures can encode every kind of universe. A simple structure might describe a simple dead universe. A more complex mathematical structure, like the one involving M-theory and quantum mechanics that our physicists study, describes a complex universe like ours, capable of hosting observers. In the Level 4 multiverse, every other multiverse we've discussed can be found. It is the ultimate ensemble of every kind of reality. In this mathematical universe hypothesis, the mathematical structure is the physical reality. We, as observers, are just self-aware substructures within this giant mathematical object. Our reality is just the view from the inside. We now rest at the very edge of speculation. We started our journey by peering over the horizon of a small map, wondering what was beyond. We now find ourselves gazing at the very meaning of reality and wondering about our own existence. What is clear is that the multiverse is not a single concept. It is a grab-bag of ideas, some built on solid science, Level 1, some on well-motivated theory, Level 2, and some on the deepest paradoxes of science, Level 3 and 4. Discussions of the multiverse often end in shouting matches. For some physicists, the multiverse seems inevitable. Ideas like eternal inflation and many worlds are simply too alluring, too mathematically clean to be wrong. But others vehemently oppose the notion. To them, talking about universes that are forever beyond our grasp is fundamentally unscientific. Ideas, they tell us, are only scientific if they are falsifiable, amenable to testing. But in truth, neither side holds the scientific high ground. In reality, our multiverse ideas are simply too early in their development. Some of the foundational mathematics might be in place, but so many mysteries still abound. We have no idea if the multiverse will be forever off limits. Some have suggested that patterns might be written into the sky, in the cosmic microwave background, bruises from an ancient collision with another bubble universe. The search continues. But for now, however, contact or hard evidence of these alternate worlds is little more than wishful thinking. We simply have no idea if the multiverse will ever be spied through our telescopes. In reality, the multiverse may be forever hidden within the fog that Edward Quinn tried to banish. We have not vanquished the clouds of ignorance. We have only just begun to appreciate their true and perhaps infinite scale.